So if the excess charge that generates the driving field is not inside the wire, but on the surfaces of the wire, then how is that excess surface charge distributed, on which parts of the surface? We can investigate that by considering here surface charge on the wires before and after they are connected. Now these diagrams show a capacitor here, but we could imagine just replacing that capacitor with, say, a power supply, a battery. So let's make it a battery, like so. Driving current around this loop here, or at least it would drive current around the loop once the loop is completed. In this picture here, there is a gap in the wire, so the switch hasn't been closed yet here, so we don't have a closed loop. So we expect that there's just going to be excess positive charge around the surface of the wire that's connected to the positive terminal of the battery, and then excess negative charge spread around the surface of the other wire connected to the negative terminal of the battery. But then once the switch is closed and current then flows in this clockwise direction around the loop, we can achieve that by, let's see, here's the argument, I suppose. We'll have a high concentration of excess positive charge here nearest the positive terminal, and then that layer of positive charge sort of diminishes as we move around this way. So a surface layer of charge concentrated nearest the positive terminal, then diminishing in strength until we get to about the midpoint of the wire, at which point the surface charge is decreased down to 0 and then transitions to becoming negative. And we'll get a high concentration of excess negative surface charge near the negative terminal of the battery, which then decreases going around this direction. So we still have a system that's net neutral overall, but we can drive the current with this distribution of charge. And this illustration down below helps explain why this distribution generates the field inside the wire that we want. So let's see. In this picture, we've got field going to the left in this wire. Down here, we've got field going to the right through this wire. So this diagram is sort of flipped opposite of this diagram here. Down here, if we've got field going to the right, we can generate a field going to the right if we have a sort of collar of positive charge here, and then a collar with less positive charge there, followed by a collar of negative charge here, and a collar of more negative charge there. This is possible because at this point here, between these two collars, these two surface charge rings here, the field from this ring at this point would point right, and the field from this ring at this point would point left, but the net field will point to the right if this ring has a higher charge density than this ring does. So these two positively charged rings can produce a net field to the right as long as this one has a higher surface charge density than this one does. Now, in between these two rings, both the positive ring and that negative ring are both going to generate fields pointing to the right. So they will sum up, making a net field to the right. And then over here, between these two negatively charged surface layer rings, let's see, at this point here, this ring produces a field to the left, but this ring produces a stronger field to the right, so the net field at this point can be to the right. And thus, we can get a uniform net electric field all the way down this straightaway if we have this sort of hierarchy of charge rings. Strong positive charge to weaker positive charge to weak negative charge to strong negative charge. So consider this set of example problems down here. You should consider the direction and strength of the net electric field at a point midway between each pair of these rings. So maybe pause the video for a moment and consider that question. Did you pause it? Are you doing it? All right, I've had my sip of water and I'm back. Rank the net field at the center of each of the pairs of rings of charge. All right, here, two positively charged rings that are, looks like the same strength positive charge. So those are going to produce electric fields that cancel out right in the middle. Here, positive ring and a negative ring. Okay, they're both going to produce fields pointing to the right at a point in between them. Next one, two positively charged rings that are the same strength. The field midway between them will cancel out. Here, we'll have a positive ring and a negative ring, both producing field to the right. And here, the last one, the positive charge, the ring on the left produces a strong field to the right. The ring on the right produces a weak field to the left. So the net field is going to be to the right in that case. Okay, so our principle is that a stronger surface charge density concentration can sort of overwhelm a nearby weaker surface charge density concentration, even if they're both the same sign. All right, so if this is how we can generate a uniform electric field inside the wire with layers of surface charge of varying density and sign, then how about the corners specifically? How do we get electrons to sort of, turn a corner and follow that wire around? Let's answer this question. What makes the current turn at a curve? So suppose here we've got electrons coming in from this end, and we want them to take a turn around that curve in the wire. Let's draw a path that they will take. And picture that curving path as being part of a circular arc. So that arc is going to be a part of a circle of radius little r, let's say. That'd be the radius of curvature of this arc. So we could sort of apply what we know about circular motion in this case. Now, if we've just turned this current on, so this is one of the first electrons moving through this region, and there's no surface charge layers built up yet, then this first electron is likely to just accelerate directly to the left until it crashes into the wall over here. And it might sort of pile up on the wall there, producing a little layer of negative charge on the wall where electrons are just piling up. And as that pile up grows, then a later generation of electrons approaching that, coming down this same path, that now sees this layer of negative charge there repelling them. So this latecomer electron might get repelled somewhat by that bumper and then maybe crash into the wall over here instead. And so these next generation electrons get repelled a bit and then crash down here, sort of building up a layer of negative surface charge there. And so all this pileup occurring here, which is probably being driven by a surface charge layer like that here. This pileup sort of builds what we can think of as a bumper. A buildup of negative charge that's going to generate an electric force pointing towards the center of this circular arc. The electric force on incoming electrons being opposite the direction of the electric field produced by this bumper here. So an electron coming down, a sort of a late generation electron coming down this path is then repelled by this well-established bumper and can navigate all the way through this path via a centripetal force, keeping it in circular motion. If we write down N2L, then the radial acceleration of that latecomer electron will be given by the electric force produced by that bumper of negative charge. And we could set that equal to its v squared over r, its centripetal acceleration, where v would be our drift velocity. So minus our drift velocity squared over little r, the radius of curvature of this path. So we can actually use Newton's laws to steer electrons around bends and turns in wires if we allow time for the early electrons to just pile up and crash and build these bumpers. Now let's look over here on this side. Let's say if this wire was this particular turn here, then let's look at this turn down here as an electron navigates around and then takes this turn through this positively charged, or this portion of the wire where the surface charge layer is a positive charge. How does that happen? What we'd expect here is that electrons coming in this way might initially, a layer of electrons that's here might move away from that part of the wire, leaving sort of a lack of electrons on that part. Since we have a surface charge layer up here that's pulling the electrons forward, up closer towards the positive terminal of the battery. So these surface charge layers are going to be pulling electrons towards them, pulling them up this way, leaving an excess of positive charge inside here. So this is sort of like an attractive bumper. I think it's not really a bumper, but this attractive patch that can exert a centripetal force. On latecomer electrons that arrive once these patches have built up from early electrons leaving this region, departing this region. So we can get electrons to navigate through a turn with excess negative charge on the outside of the curve, repelling them, or excess positive charge on the inside of the curve, attracting them. Either can produce that centripetal force that we need.